Okay then, hello gentlemen. So, first thing on the agenda that I would like to talk about is that basically we've got 2 weeks left, right? There is one day technically in May that we are supposed to meet, but I'm not gonna, unless I decide to put the last quiz on that day, I'm not gonna force you to come in that day. With that said, that means that we've got 2 quizzes left, but 3 topics. So, with that said, what I really want to ask is which one you guys feel would be the most beneficial for you? Do you believe that basically covering more information on waves and phenomenon like sound and the like would be more beneficial, or more welcome, and more information on thermal energy and things like the ideal gas laws would be more beneficial?
I guess I'll start. Maybe I was thinking thermal energy would be a
Thermal, you said?
good one to continue on with. Yeah, that would help me a lot.
Okay. Any other votes before I call it that?
I say
I
thermal.
think thermal energy sounds best.
The vast majority are saying thermal, it sounds like. So thermal it is. With that said, there is a homework due today. Let's go over some of the problems, get some feedback before we move on to expanding our understanding of the ideal gas laws, right? So, who wants to start off with asking questions?
Wouldn't mind going. Can we go over? Give me 1 second. Chapter 12, the applied concept, number 1.
Just a second while I pull it up. 12, Applied Concepts 1, correct?
Yep.
Welcome. Okay, so 12, Applied Concepts 1 says, instead of carrying a full-size spare tire, many automobiles are equipped with a significantly smaller spare tire, with warning that the car should not exceed a speed of 50 miles per hour. Okay, how much pressure does the smaller tire withstand if it must support 1/4 of a 1650 kilogram minivan, and its area of contact with the road measures 8.26 centimeters by 15.9 centimeters. Okay, so what it's asking is about pressure. And pressure, we recall, is defined as force divided by area. Force divided by area, right? Is pressure. So with that said, what we need to do is we first need to convert that weight into a force. Then, because there are 4 tires, we divide it by 4. That's what it means that it only has to basically hold up 1/4 of that weight. And then the last thing is, once we figure out the force, we divide by the area. But be careful, okay? You don't want the area of 1 centimeter squared. You want your final result to be in pascals, which is our metric unit of pressure, which is, just double check, I believe it is. Yeah, it is 1 Newton per meter. Okay, so with that said, 8.26 and 15. This is how it should look, where we have our mass times gravity for the total force divided by 4, because we only need 1/4 of it. Then we want the area, which is going to be length times width. Because we are converting to meters, it is 0.0826 meters for the one and 0.159 meters for the other. Throw this into the calculator. Oh, G is gravity like always, so 9.81. And I get something like 308,000 pascals. Now, that might sound huge, but it turns out that a pascal is actually a really tiny value. A lot of times you will be dealing not with like 1 pascal when we talk about our pressure. You will be dealing with kilopascals, which are thousands of pascals. Okay, so this sounds huge. It's not that huge. I mean, it's still large, being a minivan, but it's not unreasonable. Any questions about part A?
1 minute.
Okay.
Hey, how'd you get your answer?
Say that again?
How'd you, okay, so I'm trying to figure out how to put this in a calculator so that way I get the same number.
My suggestion would be put an extra parenthesis here, and
Okay.
G is 9.81. Okay. Which means that you need an extra parenthesis here. Any other questions?
Hey, David.
Yeah, what's up?
I got 3.078 times 10 to the 5th. Is that the same thing?
Yep, same.
Okay, thank you.
The 7/8 indicates a rounding error somewhere, but that's rounding error.
Okay.
Any other questions?
What was the answer again? What was the answer again?
The 308,117 pascals. Okay, so then on to part B. B is basically the exact same thing. We just have a different area on bottom, okay? And so once again, we have P equals F divided by A, where F is 1,650 kilograms times 9.81 for gravity, divided by 4 because there are 4 tires. But this time we have the full-size car tire, and so the area changes. We have a contact area of 15.2 centimeters by 21 centimeters. So that's 0.152 times 0.21. What was it again? Nothing. So times 0.21. Throwing that into the calculator. Oops, that's not typing in backwards. I get instead 126,744 pascals. Okay, so a significantly lower pressure. That's because this is the same force applied over a larger area. And so if my denominator gets bigger, I expect my pressure to be lower. Make sense? Any questions?
Yeah, I'm with you. I got the same thing.
Yeah, I think.
Cool. Then for part C, why is it important to limit the speed of the smaller spare tire? Okay, so remember, what's going on with basically accelerating is that you are putting a force on your axle, or your engine puts a force on the gears, which then put a force on the axle, which then puts a force on the tire, rather the wheel, which turns the tire puts a force on the road, okay? And all of those combine together, along with the third law, to end up accelerating the vehicle forward, right? So the trick is that when you're accelerating, you are going to end up applying more force on the tire than just this weight. Does that make sense?
Okay.
Now, here's the thing. It's not only when you're accelerating, unfortunately. The real world has friction, and so keeping a speed requires force when dealing with real scenarios. Okay? The higher the speed, the more force required. Okay? And so you are putting more and more force on that same small tire if you are already at a significantly higher pressure because of the smaller area. If I increase this force, I'm going to continue to get larger values than this one, right? So you want to minimize the speed and the acceleration that you apply on the smaller tire so that you don't break it, okay? Because you're going to have, at any point, a much higher pressure. Make sense?
Yep.
Questions? No. Then let's do another problem.
It is chapter 1 minute.
Chapter what now?
I just said 1 minute real quick.
Oh, okay. Anybody else have questions while we wait?
I believe it is chapter 13, review problems 1.
Okay, one moment. Okay. So chapter 13, review problem 1 says, find the pressure in kilopascals at the bottom of a water-filled drum that is 3.24 meters high. Okay, so I've got, or let me erase this and then I'll draw. So I got this drum of water. It's filled with water. And we're saying the depth of the water is 3.24? 24, yep. Meters, right? Okay. But we want the pressure, which is again, force divided by area, on the bottom of the drum. How can I find this? The answer is I apply Pascal's law, okay? Where we said that according to Pascal's law, the total pressure on a fluid, okay, that's sitting still, okay, should be whatever pressure you're applying through like a piston or the like, but we just got a barrel of water. We're not applying any pressure, so we're not going to worry about that one right now. Okay. Plus rho g h. Okay. Where rho is the density of our fluid, g is gravity, and h is how deep we are. Now, here's the thing. It said it in a weird way, but it actually told you the depth. Okay. It's told you the height of the barrel, but if the barrel is full, that's also the depth of the water. Does that make sense?
Okay.
Okay. So we have H, we have G, and here's the thing, it's water. Okay. And you can look up the density of water. The one that I always keep memorized is that the standard density of water is 1 gram per cubic centimeter. Why 1 gram per cubic centimeter? Because that was the actual original definition of the gram. How much mass is the water fits into 1 cubic centimeter. However, we generally prefer to deal with density in cubic meters. So converting from cubic centimeters to cubic meters, you multiply by what? That's 100 times 100 times 100.
$3,000.
Say that one again.
Wait, 100 times 100 times 100?
Yep.
One minute.
It's a million, right?
Yep.
Okay. So rho is a million. Oh, I'm sorry, a million grams. Be careful. So we want not grams, but kilograms. So divide by 1,000. So it's not a million, it's 1,000 kilograms per cubic meter. Okay, there's rho. G is still, as always, 9.81. And H is what we were given. And so I just multiply these two together, get my answer.
So we do the 1,000.
And I get 31,784.4 pascals. But the book specifically asks for it in kilopascals, so I divide by 1,000. I get that's equal to 31, and I'm just going to round it up to 0.8 kPa. Make sense?
Yeah, I think I got the same answer. Okay, so I got
Okay. It's all based off of this Pascal's law right here. Questions? No. Then do we have any other problems that you'd like me to do? I'll do a couple more before we move on.
it is also chapter. Also, it's also on chapter 13 and number 14.
14?
Yep.
Okay. It says, the pistons of a hydraulic press have radii of 0.54 centimeters and 0.35 centimeters, respectively. A, what force must be applied on the smaller piston to exert a force of 4,350 newtons on the larger piston? Okay, so this is all about that Pascal's law with hydraulics, right? And we said that the easier way to look at this is not by playing around with Pascal's law, but to remember that your hydraulic press is another one of our simple machines, right?
Okay.
So what does the hydraulic press trade off? It does a trade-off between basically surface area, force, and distance that you have to push on one piston, okay? Such that Can I erase all this?
Yeah.
What happens is that when I push down on this side, I end up applying a pressure. Basically, I have my force applied over the area of the piston, okay? Up on this side, I will get the same pressure, okay? P in equals P out. Now, this is a result of that Pascal's law that we just talked about, which says that for any given height, any given depth into the fluid, the pressure has to be the same everywhere, okay? Or else fluid would fall due to Archimedes' principle, or it would rise due to Archimedes' principle, right? Sink or float. And you'd have a current. And so I guess I should have mentioned, for any fluid that is not moving, for any static fluid, the pressure has to be the same everywhere within it, okay? Or everywhere at the same depth. Now, with that said, I can get the same ratio here as over here by having a much smaller force, okay? If I've got a small force divided by a small area, that's like, say, taking, I don't know, 0.5 divided by 0.5. Can we agree that 0.5 divided by 0.5 is going to be the same as, say, I don't know, 50 divided by 50? They're both equal to what?
Yeah.
1.
1, right? So these two pressures are the same, despite the fact that the forces are much different, okay? And that's what's going to happen with this problem, where we're actually setting up exactly this ratio. We say that F in divided by A in equals F out divided by A out, okay? Now, we're given F out, and we're given the radius of the two pistons, and so we can find the areas, okay? The force out is, there it is, 4,350. The area is going to be pi r squared because it's a circle. It gives us the radius of the larger one, 3.5 centimeters. And for the smaller one, 5.43. I think I'm dropping the number there, just a second. 3.53. There we go. Squared. Hit the squared. And on this side, we have the force that we're looking for divided by pi, and our new radius squared. So 0.00, because it's a fraction of a centimeter. I believe it was 543. Yeah. Okay. So in order to find question mark here, I multiply both sides by that area. Okay. I get so this is that area here times our force, all divided by this area. My pi's canceled. I'm going to just plug this into the calculator because at that point it's just numbers, right? It'll give me question mark, the force that I'm looking for. Okay, plugging that in, I get, I'm just going to round up to 103 newtons. Okay. Questions about that so far?
1 minute. I will let you know here in about a second.
So that's A. Okay. Okay, so B, they actually really probably should have asked before A. The order that they ask these questions is a little bit odd. B just asks, what's the actual pressure on the two pistons? Well, we already said that the pressure has to be the same on both of them, right? That's the entire premise of this equation. And so all I really have to do is this right here. So just type this into the calculator and you'll get out your answer. So B Okay, I got 1.1 continual times 10 to the 6 pascals. Converting that into kilopascals, that's basically 1,111 kilopascals. C,
Hey, David.
what's up?
I left it in, or I got it in Newton centimeters.
You don't want that.
Yeah.
Pascals, trust me.
Okay.
This statement here for the radius, I've converted this into meters. And if you convert this into meters, that gives you pascals, okay? Which is our standard unit.
Okay.
Easy enough?
Yeah.
Cool. Let's see. Part C says.
That's mechanical.
What is the mechanical advantage? Well, mechanical advantage, our definition was F out divided by F in. We solve for F in up here, so we have, where did it go? 4,350 divided by 103, and that gives me 42.2. That doesn't have units. Mechanical advantage doesn't have units. Okay, so did you have any questions about this problem?
No.
I think I might be good.
Okay. I got time for one more before I move on.
Perfect.
Unless somebody's got another one, I was wondering if you could go over 13, question 9.
13, question 9. Okay. What must the water pressure in kilopascals be on the ground to supply a water pressure of 252 Newton centimeters squared on the 3rd floor, which is 9 meters above the ground? Okay, cool. So I'm going to erase this and then I'll start on that one. Now, the first thing that we need to do is convert that thing in newtons per centimeter squared into pascals. But other than that, turns out that we're just going to apply that Pascal's law that we learned again. Okay? And apparently I need to clean my eraser. And it's okay, I got a backup for now, but I'll have to remember to do that at the end of the night. Much better. Okay. Anyhow, so what's going on? We got some sort of pump here at the bottom. It has to apply pressure all the way up to the top. And we've got some shower head, and it's spewing out water. So the idea is that we have a pressure up here of, what was it? 252 newtons per centimeter squared. Okay, so as I said, let's start by converting this to pascals. Okay, so just like what we did with converting from centimeters to cubic centimeters, we do something similar to get from centimeters to square centimeters. What's 100 times 100?
1,000.
10,000, right? Okay then. So I take my 252 and divide by 10,000, and I'll get how many pascals I have there. There. Oh, I'm being silly. Multiply, rather, by 1,000, don't by 10,000, don't divide. And then we're going to divide by 1,000 to get kilopascals. Times 10,000. That gives me 2.52 times 10 to the 6. Divided by 1,000 to get to kilopascals, and I get, that is 2,500. That's at the top, okay? So here's the thing. In order for the pump to provide that pressure up here, it has to provide that pressure plus all the pressure lost pushing it up, okay? Basically, what's going on here is this is the pressure at the top. What is the pressure at the bottom is what the question is asking, okay? Does that make sense?
Yeah.
Okay. So with that said, that pressure is my total pressure, which was that E applied plus rho GH. Here's the good news. This is E applied. Okay? And we already know what rho is. We already know what G is. And it gave us H, right? So rho is, again, because it's water, 1,000, right? G is still 9.81 like always. and h it said was 9. Okay? So I multiplied these three together. I get that's 88, we'll just call it 0.3 kVA. So 88.3 plus 2,520 gives me whoa. Oh, I see what I mean. There we go. Okay. Any questions about that one?
So we multiply it by the 2,520, correct? By
No,
yeah.
you add 2,520. Add.
Yeah, that's what I mean. The applied force, and then you multiply that by the like the 88.3 and stuff because in kilopascal.
Okay. So I take my applied force, which is this value,
Okay.
and add this. So it's
Okay.
this plus this. So here, I'll write it out as the other. That's 2,520 plus 1,000 times 9.81 times, sorry, that's times 9.81 times 9. Plus, not, this is where you multiply together. Make sense?
Yep, I got it.
Okay, any other questions? No, okay then. One last thing that I want to mention before I get back over into thermal is I was grading the one lab about Archimedes' principle, and I saw a little bit of a misunderstanding that I may have introduced with my wording. Okay. Buoyancy is the name of the phenomenon, the event, the occurrence, whatever you wish to call it, where things float. When I'm dealing with what forces are present, what forces will cancel out, etc., it's specifically the buoyant force. Okay, so I saw a couple of wordings that got a little bit jumbled and a little bit confused because people were getting the idea of buoyancy, the event, and the buoyant force mixed up. And what's going on with floating is that an object floats, if you recall, when the force due to gravity down is equal to my buoyant force, which I'll call F sub B, up. Is when it floats. Where F sub B is the mass of the water displaced. L.
So your boat achieves buoyancy when the mass of the water that is displaced by the mass of the boat are in equilibrium?
Floats is the way that we phrase it. Boat floats when the mass of the water displaced is equal to the mass of the object.
Okay.
Okay?
I think there's actually
Okay.
write that down actually.
If the volume of the object is not large enough to displace enough water, to push enough water out of the way, such that the mass of the water displaced equals the mass of the object. If the object is too dense, if it does not have enough volume to push enough water out of the way, then it sinks. Okay? Because the mass of gravity then is still bigger. It is not equal if it sinks. Does that make sense?
Okay.
Okay. The force of buoyancy is never larger than the mass of gravity. Well, no, I'm sorry. Let me change that statement. The force of buoyancy, the buoyant force, is only larger than gravity if you take something that would float, like say a ping pong ball, okay, and push it all the way under the water. Okay, that's what you should have been seeing in that lab when you tried to push the wood all the way under. You saw that the force of buoyancy was much larger than the gravity force, and that's
Yeah.
when it would basically pop up. Okay, make sense?
Yeah, a little bit.
Rise to the surface. Okay then. I just wanted to clear up that misunderstanding that I was seeing throughout people's lab. Then, with that said, let's do a quick recap of the ideal gas laws. So, or rather, the ideal gas law. But who wants to start me off with kind of describing what's going on with the ideal gas law before I write it up there?
Hold on a minute. Okay, get to that chapter.
Okay, so let me start you off then, because people seem to be kind of forgetting what's going on. We said the ideal gas law is a lot like Bernoulli's law. And what we're doing is we're taking our pressure, which we said was kind of like our energy density, okay? But here we're then multiplying it by the volume. And so what's the density? The density of something times its volume. The total, right?
Yep.
So if I take my energy density times the volume, I get my total energy, okay? So basically what's happening is I said that E thermal equals my pressure times my volume. But it turns out that there's another way that we can find our thermal energy, right? What was the other side of this? Here's a hint. What's going on with specific heat? What was specific heat all about?
There's what?
What was going on with specific heat?
Say that again.
Okay. What was going on with specific heat? What was specific heat all about? Wasn't the idea of specific heat that if I have a heat of some material that has mass m, then the amount of heat, the amount of thermal energy needed to increase the temperature by a degree is the mass of the object times some constant, my specific heat, times my change in temperature, right? Well, what if I remove the deltas? What if I'm not concerned about the change in, but rather the total heat contained, right? The total, or rather, total thermal energy contained. Be careful. The heat specifically deals with change in temperature. Well, then I can indirectly get rid of this delta. But in order to get rid of the delta, I really kind of want to look at not specifically the mass times C, but I actually want to look at my number of particles, okay, n. Because we said that what's going to happen is that T T is related to the average velocity of my particles, correct? And in fact, it's related to the root mean squared, okay? Which means that it's related to the velocity squared, okay? And so I can think of this kind of like asking, well, what's the average kinetic energy of a given particle? And then we're going to multiply it by how many particles we have, okay? Well, we know that that depends on the mass. We know that that has a factor of a half. We know that that depends on how much they might be attracted to each other or not. We know that depends on a number of different factors, right? So the good news is the ideal gas is a very specific scenario, okay? Such that when we're talking about the ideal gas, we end up condensing all those different factors that we talk about into a single constant. I'm going to change this to lowercase n, and I'll explain in a second why. That constant is R, our ideal gas constant, times T, okay? Where R absorbs all those other variables that I was just talking about. So why lowercase n instead of big N? What does lowercase n indicate? Who can remind me?
You're asking what is the lowercase n?
Yep, what does that variable stand for?
Is it smaller than newtons, right? But it's the same. It's a type of force.
No, no, no.
No.
My number of moles. Okay. We
Oh,
said
okay.
that for any macroscopic, that is to say, any object that you see on a day-to-day basis, turns out that there are a lot of particles. A mind-bogglingly large amount of particles, okay? More than you could count in your lifetime. And so we basically chose a material, the arc constant. It's actually carbon 12, okay? Where we said that 12 kilograms of carbon 12 would be our constant, our unit for number of particles, okay? And the number of particles that is in 12 kilograms of carbon 12 is 1 mole, okay? And it turns out that that number of particles, there's a little bit of leeway because of, you know, our accuracy in measuring 12 kilograms. It should be Avogadro's number, which is I always forget which one's 20, 33. Give me just a second. This is the one that's 23. .02 times 10 to the 23rd particles, okay? So remember, 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion. This is 10 to the 23rd, okay? This is bigger than anything that you've ever basically encountered. There's a huge number of particles and things. And so instead of dealing with the number of particles directly, we often deal with the number of moles. Does that make sense?
Yeah. What is a mole again? 1 mole?
1 mole is this many particles.
Oh, okay. All right.
Okay.
equals 12 kilograms.
Specifically, it's 12 kilograms of carbon-12, a specific isotope of carbon.
Okay.
Okay. Any other questions?
No, I think I'm good.
No. Okay. So with that said, basically, all that we did for our ideal gas law is said, well, if this is one way of finding all the energy contained, and this is one way of finding all the energy contained, okay, they're just set them equal to each other. That's my ideal gas law, okay? Now, here's the thing, and what I did not go into a bunch of depth about is that it turns out that when I go and I actually start to change my values in here, I can do different things with my container or with heating or cooling my gas inside in order to hold one or more of these variables constant, okay? Usually, what we do is we almost always end up holding n constant. We usually don't worry about increasing or decreasing how many particles are inside of the container, okay? With that said, I do ask you in the lab that I'm going to basically assign this week to play around with how many particles are inside the container and see what happens. But often what occurs is we have some constant value for n, and we pick one of the other three values here that change. Remember, r is always a constant. It's equal to let's make sure that I get the same one that I had last time. We want yes, that one. 8.3. Okay. So R is always 8.314, provided that we have this in moles and this in Kelvin. Okay. So pick one to keep constant. P, V, or T.
Let's keep P constant.
We're going to keep P constant. So what's going on is we have a container, okay, that's going to basically expand or contract in order to keep our pressure constant. Easy way to think about this one is it's something like, say, a balloon, okay? What's going to happen is the balloon, it's rubber, right? And so as it expands, it's going to basically keep its total pressure constant, because it's going to basically have an increasing surface area, but increasing force on that surface area, okay? Does that make sense? So
far.
if I heat up the particles, if I increase T, if P doesn't change, V has to increase in order to keep the two sides equal. If I heat up my balloon, the balloon's going to expand. Make sense?
Yeah.
Okay. Let's take another one. P or T? Oh, I'm sorry. We started with P. V or T? Which one do you want to talk about next?
V is in Victor.
V. So keeping V constant is something like one of those big gas cylinders that you see. The volume of the gas cylinder certainly is hopefully not changing, right? if the volume of the gas cylinder changes, something has gone hideously wrong. And so in that case, V is constant. But if you ever look at the gauge on your gas cylinder, right, you can get that P up really high, or you can basically release the gas to get it all the way down to 0, okay? So what's going to happen with the gas cylinder is if I increase T, okay, P is going to increase to compensate. If I get the gas inside hotter, it's going to increase the pressure on the cylinder, okay? Questions about that one?
So wait, what did you say again? So you said that if you increase T,
Increasing the temperature increases the pressure in this case. If we
Okay.
keep our volume constant, because it's a metal cylinder, increasing the temperature increases the pressure. Make sense?
yep.
Excellent. So then that leaves keeping T constant, right? Well, if I keep both N and T constant, that means that this entire side isn't changing. What's going on is we're playing around with basically, say, letting the gas expand or taking the gas and compressing it, okay? Well, if V decreases and T stays the same, then P has to go up, okay? So if V goes down, P has to go up to keep this side the same. Vice versa. If V increases and this side stays the same, then P has to go down in order to keep that side the same. Does that make sense?
Okay.
Okay. Any questions with this ideal gas law?
No, I'm good.
No, we're good. Okay then. Let me just flip through, make sure that there's nothing missing in that chapter. And then, if not, I'm actually going to skip back and talk a little bit more about the previous chapter before moving on to waves, seeing as you said that you wanted to have the last quiz about this chapter, about these two chapters.
The last quiz is I know it's gonna be over thermal, so is it gonna be under like over like temp like the thermal and stuff and gases?
Okay, so just to be clear, this week's quiz is going to be about fluids and pressure.
Yep.
Next week's, which would be the last one, right?
Yeah.
Okay. Next week's quiz would be about thermal, which would be chapters 14 and 15.
Okay.
Okay.
And that will bring us to the end of the semester.
I will double check that nothing has changed about that, but I'm pretty sure. We'll just pull up the academic calendar.
'Cause I mean, I didn't see anything that's changed about that, but
I believe the last day is May 4th.
Yeah, I have another class that's ending on the 2nd.
May 4th. So the 30th is our last day. I thought it was May 5th, which would have technically made the 5th the last day, but I was going to say don't bother. If the 4th is the last day for all classes, then the 30th is the last day for this class, okay? So the last quiz will be not this week, but next week,
okay. So
okay?
we're gonna have this week and next week's quiz. Okay.
So
This
would we
week will
then
be
have-
about fluids and pressure. Next week's will be about thermal.
So then are we going to have homework for next Tuesday then?
Yes.
Okay.
The reason why I was asking you about that today is so that I could select which homework to do, whether I should have written homework about waves or homework about thermal. So I'll write up a homework about thermal and post it tonight.
Okay.
Yep. Okay. Any other questions about basic class structure before I move into basically more questions about thermal.
No, I'm good.
Okay. It's mentioning something. Oh, okay. Yeah, I'll mention that briefly. The book does like to talk about one of this chapter. And it goes like this. So if I have a container of particles, right? Okay. And they're all moving around, they're all bouncing around, such that they fill as much space as they can. Okay. If I shrink my container without changing the number of particles contained, what's going to happen to the density of particles? Well, what's going to happen is, because I've got a smaller container, the same number of particles, that density is going to increase, right? They're closer together. That means the number of particles per unit volume is larger. That means the density is larger, correct?
Yep.
Aha. So this deals now with what we call a compressible fluid. If you recall, going back to our chapter about fluid flow, we had said that if we have our continuity equation, that one about the volume, or rather the velocity, times A in equals velocity, and this is serifs for volume, sorry, out times A out. That was all dealing with an incompressible fluid. And we said that most liquids we can basically describe as incompressible. You can't really squeeze them much, okay? Gases, on the other hand, we're all familiar with the idea of an air compressor. Gases generally you can compress. You can change the density of your gas, okay? And what is suggested is that because we're keeping the number of particles the same, that my density is just N divided by V, right? V for volume, so the serifs. And so if I look at my pressure compared to my density, and recall that statement about energy, well, we know that in order to keep the energy constant, P times V at the start has to equal P times V at the end, right? Because we said that P times V gives me my energy. And so energy at the start has to equal energy at the end. Energy is conserved, right? Okay.
For some gases, more.
Speak up. Just say that again.
Are some others
Sounds like you're having mic problems.
than
Were you saying some gases easier to compress than others? If you're asking about if some gases are easier to compress than others, then the answer is yes. One thing that I did not address earlier directly was what's known as viscosity. Okay, I had it in one of the homework problems. I'm surprised nobody asked about it. But viscosity is basically resistance to flow, a fluid's resistance to having its particles move out of the way or move along. Okay. Viscosity depends on a number of different factors, but gases can have a viscosity as well. Okay. It's fluid flow, not just liquid flow. By that same concept, some gases, because of a lot of the same properties, are easier to compress than others. The good news for this particular problem and this particular set of questions is we are dealing with the ideal gas. Okay, and so it's all the same gas, more or less. I am not adding in the complication of having two different types of gas, having two different masses of gas. Your book does not, and so I'm not going to have you cover that yet. Okay?
Okay.
Okay, cool. If we end up having a lot of extra time, I will cover that topic. Anyhow, back to this. Right. That means I can rearrange this to say, right? Where all I did was divide this E over the other side, divide this P over the other side, okay? So these two statements are the same. Now, I'm gonna pull a trick, okay? And that trick says that, well, we said that for both containers, I have the same number of particles, okay? And so one of the tricks that you can do in algebra is you can multiply any number you want by 1, okay? You can multiply any equation that you want by 1, because multiplying by 1 doesn't really do anything. It doesn't change the equation, right? Well, right.
Yeah.
Okay. It turns out you can also multiply by anything equal to 1. Any little equation equal to 1. And so what I'm going to do is I'm going to multiply by n divided by n, okay? Because anything divided by itself is 1, right? Then what I'm going to do in order to make this come out the way that I want is I'm going to take this 1 that I multiplied in and I'm going to distribute it in a weird way, okay? I'm going to actually distribute it like this. Sorry, I ran out of space in the bottom. N divided by my final volume divided by n divided by my, wait, let me just make it quick. Yes, I did. Okay, quick correction. Because I flipped it, made an algebra mistake. Yes, I can see this. This, okay? N divided by V start divided by n divided by Vn. Here's the thing, there's actually two algebra tricks there, and that's why I have made a slight algebra mistake, okay? So the second algebra trick goes like this. What is 1 divided by 1 divided by 2? If I put my parentheses here, what is that equal to?
What was it? 1 divided by 1.
Divided by 1 divided by 2. If I have my parentheses here, what is this equal to?
1 divided by 1 divided by 1/2.
So yes,
Okay.
1 divided by a half.
Half,
and 1
which is
divided by
1/5.
a half is equal to what?
Half.
Wait,
Wait.
say that again.
But anything divided by a half
1 divided by a half is what?
is 1/2. Yeah, 2.
2.
Double.
2. Okay, 2. Okay, so the trick goes like this. If I have a fraction in the denominator, a fraction in the denominator is the same as taking that denominator of that fraction and multiplying by it. I could say 1 times 2 is equal to 1 divided by a half. Does that make sense?
Okay.
Okay. So what happened here is I said Vn, well, that's like taking 1 times Vn. Instead, I can take and divide by something where Vn is in the bottom. Does that make sense? Just like I did with the 2.
Hold on, repeat that last part. That
Yep.
last part was getting a little bit confusing.
So, can I erase this here?
Yeah. Yeah. I'm good.
I'm just going to add in a step so that you can see what I did.
Okay.
So that step says this. Vn times 1 is equal to 1 divided by 1 divided by Vn, right? Making sense so far?
Yeah.
And another trick that I can do is for the bottom here, 1 divided by the start is equal to 1 divided by v start times 1. Right? Basically, instead of having a number divided by something else, I can just call it a fraction times 1. Right?
Okay.
Then, what is this 1 in each of those cases? This 1 in each of those cases is the n divided by n. Okay?
Okay.
So if I replace that 1 with the n divided by n, such that I have, let me just fix it all up. So using these two concepts, I can write this here as 1 divided by v start divided by 1 divided by v end times n divided by n. This statement here is this statement here. Okay?
Okay.
And to get to this final result, or to get to this result, I take this n, and multiply by that, and this n multiplied by that, such that I have this statement here. Questions?
Okay.
Okay. So what was the point of all this algebra, right? Why bother? Why bother is that n divided by v start is defined as my density at the start. N divided by v end is my density at the end. Okay, such that the end result that we wanted is that these two are equal. A lot of algebra to get this equation. And just to give you the conceptual explanation one more time, the idea goes that, well, if I do that same thing where I decrease my volume with the same number of particles, right, they're basically going to be hitting my container more often. They're going to increase the pressure, right? Or alternatively, you can say that energy is conserved. So if the volume goes down, the pressure has to go up, right?
Okay.
And so my pressure at the start is related to the density at the start, and my pressure at the end is related to the density at the end. So if I look at the ratio of beginning to end, the two ratios should be the same. Does that make sense?
Okay. Yeah.
Excellent. Any questions about this?
No. Good.
Okay. And that was the last topic that they covered with that ideal gas law chapter. I've got that it's 6:50, which is when class is supposed to end. I will give basically some more examples. I would like to do some more example problems with thermal. I will cover those Thursday. I would also still like to cover, as in at least talk about and do lecture on waves before the end of the class. But I will write up a homework and a quiz about thermal, and that will be the last topic that you are actually tested on.
Okay. So we won't be testing on waves at all.
No.
Okay.
Okay. Have a nice night then, gentlemen.
You
Thank
too.
you. Have a good night.
See you, David.
See you.